So I was asked to give an inaugural lecture, and I've been at EPFL for less than 2 years. So I'm not going to think about the last 6 years working with my students, because there are no 6 years working with my students. Instead, I'm going to ask a question. And the question I want to ask is, why and when can you trust a machine? Right? We run computers. When can you trust these things? And my preferred perspective to approach this question is a discipline that is called formal methods, and that's what I want to introduce today. The way I will do this is in 4 parts. I will first try to highlight the problem with software as it is written today. Try to explain why things could be different. I want to show you that software engineering, despite being labeled engineering, should actually be done in a fundamentally different way from what is done today. Third, I want to illustrate some of these ideas concretely. I'll make some general statements in part 2, and then in part 3, they'll get concrete. And finally, I want to briefly survey applications of all this by talking about my lab and what we do there. That will be very short. So to motivate this topic, I thought I'd start with a picture. And I think this picture captures everything that's wrong with software engineering as a field. A few years back, many people started putting physical shutters on their webcams, and ACM handed off little sticky plastic camera shields at conferences, and some laptops now even have the physical switch. And when you think about this, what does this say about how much we trust our computers? Right? You have a miracle of optics and engineering in the form of the camera, and then you put some tape on top of it because you're like, well, probably the software is spying on me. How much more in our daily interactions is of that form? It's just passively accepting the fact that nothing really works, nothing's really trustworthy, and everything is subtly broken. And if you subscribe to the tape on your webcam camp, please give me the solution for the microphone, because I don't have one for that. All right, so I know it's hard to care about security. I know computer security can be abstract. So if you leave from this talk with just one thing, let it be that. Your chocolate supply is not safe. That's a significant problem. Now, there's all sorts of other things that are in danger, but those are not super important, right? Electricity, nuclear, controllers, cars, toys, medical devices, more medical devices, supply chains, modeling software, hypervisors, Git, school as well, but I mean, yeah, it's not as important as the chocolate, right? More school, companies as well, and then homes, and then, oh yeah, look at the bottom, it said, la situation devrait perturber jusqu'à ce week-end, and then, well, never mind, 1 month later, things are still broken. Everything is horribly broken. So the question is, how did we get there? And for me to answer this question, we need to step back a bit. And we need to ask, how do we make things? What is the process of making a physical thing? I'd argue there is 2 phases, whether it's a suspended bridge, a solar panel, a mechanical pencil. These phases are in common. First is the design phase, which we might also call the modeling phase or the planning phase. And in that phase, in this design phase, scientists and engineers produce models of the object and of its environment, and then use these models to make predictions about how the object will behave in the world. The second phase is the manufacturing phase, which we may also call the crafting or implementation phase. In that phase, workers will implement blueprints coming from the design phase. They'll mix concrete, they'll tension cables, they'll fasten screws. Fundamentally, they are crafting items, not designing them in that phase. Now, if you think about the way software works, well, software engineering is essentially the same as traditional engineering. That is, you first design the artifact that you want to build. In our case, it'll be a program. And where other engineers use 3D models of materials and structures, well, software engineers use executable prototypes, algorithmic descriptions, or specifications. In both the software and the traditional engineering, the design phase is fundamentally mathematical. Structural engineers who design a suspended bridge will use the laws of gravity to predict whether the bolt, how large the cables need to be. And software engineers will use algorithmic reasoning to design, say, a routing application and describe characteristics of a shortest path. Second, you manufacture your artifact. So where other fields have workers polish ball bearings or tighten screws, we software developers implement things. We write computer code, we set up continuous integration, we assemble build scripts, we wire GUIs together, and fundamentally this analogy extends to the whole software lifecycle. Just like other engineers, we software engineers have best practices and ISO norms and certification, testing, quality assurance, acceptance criteria, and so on and so forth. And when you think about this sounds like a good thing, but it really isn't, and let me tell you why. The reason is that the reason this thing works is mostly a historical accident. Designing software is indeed fundamentally the same as designing bridges or solar panel. You use the fundamental laws of the world to predict what's going to happen. But manufacturing is fundamentally different because software is fundamentally different from your typical artifact. Here's a different way to view this. If we think of the process of manufacturing, manufacturing means bringing tangible objects into existence. That is, you go from models that live in the world of math and of ideas, and you go to items like elevators or mechanical pencils or so on that live in the real world. They're physical things that you can hold. That is, the process of manufacturing takes the abstract and makes it concrete. It takes the intangible and makes it tangible. Now, how does this look for software? Well, the process of programming takes specifications or high-level prototypes and brings them into software. Both of these things are fundamentally of the same nature. They're both mathematical objects. They're not tangible. They do not live in the real world. There is no fundamental distinction between specification and software except for the level of abstraction. And in fact, the process of programming is really taking the abstract to the abstract and the intangible to the intangible. Now, this observation has profound implications for the science of software because it lets us actually prove programs. And to explain what that means, I want to stop talking about things that are bad and start talking about things that are good. So what I have here is a mathematical description of what it means to look for an item in a collection. So my collection is HS for haystack, and my item is N for needle. We're looking for a needle in a haystack. And what we're asking is there an index in our haystack that contains that needle? So does there exist an I such that HS of I equals N? Good. This is not how you program. The way you program is you write a search function that says for every element in my haystack, if the element equals the needle, then return true, and otherwise return false. There's a whole field of study at the intersection of mathematics and computer science that is concerned about this duality between code and math. So formal methods allows us to transform computer code into mathematical statements. What that means is that we can connect this specification to this implementation. This is a powerful concept. You cannot prove that a bridge will not collapse. You can predict that it will not collapse, but this prediction has to be tested in the real world, and it may be invalidated by the realization of the bridge itself, right? If someone didn't tension the screws the right way, if someone didn't predict the strength of the wind in the right way, well, the bridge will collapse. But software is different. In software, you could actually mathematically demonstrate that the software matches its model. Unfortunately, you could, but almost no software is developed that way today. Instead, we continue to treat software as a traditional engineering artifact, and the results, bugs, crashes, data leaks, data thefts, I think speak for themselves. So in the rest of the time that I have, what I want to do is illustrate concretely what it means to do math about software through vignettes that are related to the research in my lab. The first one I'll do is make it actually concrete when I say we can connect software to a mathematical formula. So what we'll do is we'll take this program and we'll make some math out of it. So we'll start at the top. We notice that there's some high-level syntax in there. So what we'll do is we'll say, well, let's replace this for loop with a more concrete thing. We'll have a while loop. I starts at 0, while I is length at the end. While I is less than the length, continue your computation. But then we can actually simplify this further and say it's just while true, so forever. If you notice that you've gone past of the end of the haystack, well, just like in traditional cartoons, you realize, oops, I'm past my haystack, I'll stop here. And if you have found your needle, you'll also stop, but with a different result. And you'll continue going like this, incrementing the counter every time. We can then extract the body of this while loop into a function that I'll conveniently call loop that says, can I find my item starting at index I? But then we realize, wait, this loop can be unrolled. It's self-replicating in a sense. So in fact, I can just execute the body of the loop once and then repeat that operation starting at the next index. So now what I'm saying is just while finding something in that haystack is just trying all the indices and saying, can I find it from this index? But then now I'd have two simple conditionals, so I can actually convert them to one big logic formula, which is, when have I found something starting at index I? Well, first, I have to know that I is less than the length of my haystack. Otherwise, I'm out of the haystack and I have no chance of finding. And second, either the current element is the right one, or it can be found in the rest of the haystack. Now, rewriting this to look a bit more mathematical with bars for lengths and indices, what I really have is a logical formula. In fact, I have a pair of equations. One of them that says that searching in the haystack for the needle is just calling this loop at 0. And the other one is saying that the loop at I is the conjunction of two things. I is less than the length, and HS of I equals N, or L of I plus 1 holds. Now, this is all good, but there's still some recursion in here. So is it really math? I don't know. Let's actually eliminate that recursion too. So we take that formula at the top, and we're going to go step by step. The first thing I'm going to do is I'm going to say, hi, you know, it's logic. Is it really math? I don't know. We want to do real math. Real math is arithmetic. So let's just replace this by arithmetic. Instead of saying yes or no, we will say more than one thing is true or no things are true at all. So we will count true things instead of anding and oring them together. What that means is that and becomes multiplication and or becomes addition. So now we have this new function that says, well, the formula is written right there. Now, the second step is to say, well, we can expand. So multiplication expands over addition, no problem. So we expand that. The third step is a bit subtle. We are checking whether I is less than hs. But the first thing that L of I plus 1 will do is check that I plus 1 is less than hs. And if that succeeds, well, then, of course, I was also less than hs. What that lets us do is simplify this formula by eliminating this term. Now we have a nice and simple formula, but it still has this annoying recursion. But we're doing math and arithmetic, so just put a sum in there. So what we'll do is, well, add sums, you know, just sum over I. This can be justified. I won't do it here. But the nice thing now with the sum is that I can decompose the sum on the left into L of 0 plus the sum of L's of I plus 1. And at that point, naturally, I can cancel things so that I have a closed formula. L of 0 is the sum of i's of these two criteria. Now, when is a sum non-zero? Well, at least one of the elements should be non-zero. So we can translate that back into logic by saying, does there exist an I such that that is less than hs, such that hs of I equals n. And that, well, is the formula that we were looking for. So you can actually take a program and translate it into math. And that has profound implications. It means that we can take programs, automatically make math out of them, and then use mathematical solvers to check, does my program conform to a specification? Does it do what I want? So that's my first remark. The second remark that I want to make is, or rather the second example that I want to give, is something that is in development in my lab. And it asks us to, in a sense, rethink how we think of programming. So up to this point, I've said we have some software and we want to verify it. So we have the software, we'll translate it into math, and then we'll automatically prove things about it. But sometimes you actually want to be in the driver's seat. You want to do something that is called interactive theorem proving, and that's actually most of the focus of my research. And I'll motivate the problem in this way. Here is an extremely simple function that converts a string to uppercase. So we have a collection of characters, and for each character, we'll convert that character, well, to uppercase. The way we do that is just saying map, that means apply an operation to every character. We will map over our string the upcase function. Now, it's very simple to convince yourself that this does what you want. The problem is, it's also very nice to prove theorems about it. We can prove, for example, that the operation is saturating. If we do up of up, that's the same as up. We can prove that it commutes with reversing. So we have all sorts of nice properties that we can work with. The problem is, if I write this code in an actual programming environment, like the Coq proof assistant, I get the assembly on the right. Notice that scroll bar. This thing goes on for pages and pages. It calls a map function. It allocates a lot of memory. It runs very slow. It is not memory efficient. It's not memory local. It's not parallelizable. It's purely sequential. It's insanely inefficient. In contrast, if I were to write this in C, I would probably write some code that looks like this. There's a number of things that have happened in this code, which we'll look at in a bit more detail later. But the lesson of this code is the core loop is here. It is fully vectorized. It processes dozens of characters at a time. Depending on your machine, it might be more or less, but it processes many characters at a time. It is mutating a buffer in place, so it's not creating new lists. It's just, it just rips through this entire task much faster than the original version. And the only slight problem is the ... under the proofs. Yes, we can convert programs to math, but for this sort of program, the math looks really bad, and the proofs are really painful to me. So what we would like to do is start with this original specification and then generate that code. And to do that, in a sense, we need to capture the insights that went into writing this efficient code and teach a compiler how to use them. And the way we're going to do that is we're going to treat compilation, which is the process of translating one program into another, as a proof search problem. So what we will do is we will say, well, compiling, we have a statement that we can make, which is function f can be compiled. That's what it means for our compiler to work. And in contrast, we'll rephrase this as a proof search problem by saying that a function can be compiled means that there exists a low-level program, say a C program, such that for any input and for any starting memory in your computer, if the memory contains the starting point of your program, contains your input at some address 0, then for any memory that your program can reach by running, you will find at some output address. Yeah, so for any memory, you will find at some output address let's say address 1, the value f of x. So what this is saying is you had f, that was your model. Well, what does it mean for f to be compiled correctly? It means that this program actually takes inputs to outputs, takes x to f of x. Good. So this is a mouthful. We prefer to write it that way. It's called a Hoare triple. I believe our software construction students have seen that less than a week ago. So it's actually useful in real life. Well, is this real life? But there exists a program such that for all inputs, if you take as input x and you run the program, you should get as output f of x. Good. So let's take this. Let's make this very concrete. Let's run our. Let's use this framing of the problem to actually derive some C code. So there's going to be a lot of happening on the slides here, but fundamentally the idea is we have the theorem at the top that we're trying to prove, and we're going to prove that theorem by generating small bits of software. At the bottom will be a description of what we're actually doing in terms of so-called tactics, so the process of using a proof assistant, and at the bottom right will be the code that we're generating piecemeal. So we start by saying, well, we want to generate something, so let's put a question mark in here. And then let's actually unfold this map function. So if I just go back, what happened is we had just this function up that I had defined earlier. It was str.map. But now we can tell the compiler, hey, by the way, map is really the equivalent of a loop structure. So we will rewrite this as start with index 0 and then iterate up to the length of the string with this function that does read from the string, uppercase, put back in the string. Good. So then we can actually take this little bit of index out, and we can spawn a new sub-theorem. So we want to prove a smaller theorem that says, starting from an empty memory, can I create a location in memory that contains the value 0? And the answer is yes. That's just an assignment. If I set index to 0, then I have indeed creating that memory location. So we generate our first bit of code, int index equals 0, by proving this one theorem. Good. The next theorem that we have to prove is, well, the next theorem that we will use is this template for iteration that says if you had, going back, if you had the pattern of iteration, you can actually replace this by generating a for loop and then proving a quantified theorem that for all indices, we can actually update the string by reading from it, uppercasing, and putting it back. Okay, so we continue through that. We normalize this thing to do it step by step. We will first get. Okay, well, getting in a string is the same as reading memory. So here what we've done is we've translated between this list-based representation of list to an array-based representation of list. We fulfill this bit by just dereferencing a pointer. Continuing, we now have an uppercase operation. And here the programmer will prove an extra theorem that says it is actually correct to do this bitwise manipulation of numbers to implement uppercase. And that depends fundamentally on the properties of ASCII. It's not something a compiler could guess, but it's something you can teach the compiler that, yes, it satisfies this theorem to plug in this little assignment here. Now we have one more line in our program. Continuing, we just need to put back into the string, which is just an assignment, all good. And eventually, well, we have generated our full program on the right. So what we have here is our uppercase function. Now, this could be either driven fully manually, or it could be driven interactively by a user, or it could be but with some assistance from the compiler, or it could be fully automatic. It doesn't matter. The core functionality here is that proving the existence of a program is the same as actually generating that compiled program if you're in the right logic. And so that's what we're doing here. So what's the point of all this? Why are we doing all this? Well, the point is this, broadly. So I tried to express what my lab does as a series of arrows on this picture. Fundamentally, start at the top left. You have mathematical specifications. You can get high-level functional programs from that. You can extract those to low-level imperative programs. And then with a bit of luck, if you have the right hardware, you can actually get verified binaries that run on verified hardware. Eventually, I would like a trustworthy future. I thought I would zoom on each of these things, but the fact of the matter is I've only been here for 2 years, and so most of the things we actually do don't have snazzy logos yet. So instead, I thought I'd do it from the perspective of people. And so those are not the people in my lab, but the people in my lab who have given me a picture. So sorry, folks who are not in the picture, but there are many more people. I'm just not very good at getting pictures. Fundamentally, my lab does 3 things. We do compilers, we do systems, and then we do tools. I won't get into much detail. I just want to give you a general idea of what it means to be at the intersections of systems and formalisms. one of the first things that we did, and I'm excited about, is we looked at the semantic of regular expressions, which are these pattern matching programs. And we showed with my postdoc, Aurel, that you can actually do a lot more than was thought in linear time. So we did some algorithms work to show that you could just match more things, that you could enhance the expressivity and the performance of certain regex constructs. This one is the easiest part of my research to try. If you have Chrome on your browser, you have our code. Chrome on your machine, you have our code, so you can try it tonight at home. The second part is as part of an open research data project. We actually did that translation to math. It was not quite automated because we were not translating from code, we were translating from English. So there's 40 pages or 30 pages of English describing how these regexes are supposed to work. Well, we translated that into math, so we can now prove that. And by we, I meant a very brave master students in my lab, Noé. The third thing that we're now starting is this general project about rethinking the way we do regular expressions. So the idea here is to produce, we want to produce regular expression engines that are safe in the sense that they don't explode or have bad performance, expressive in the sense that they can match as much as possible, and trustworthy in the sense that we have proofs that they actually do what they're supposed to. Now the second thing, systems. Well, going briefly again, I have worked with Professor Bourgeat, who made this very nice intro, on systems for hardware verification, that is proving that a piece of hardware actually implements an instruction set architecture correctly. And we have recently, with some collaborators at MIT, proved that you can, or showed that you can actually prove properties like there are no timing side channels in this particular design. We have worked on the C side with John, one of my students, and a student of Professor Candia, on automatically proving, so automated this translation from code to mathematics to automatically prove properties of critical systems code. And, well, this demo that I just gave with this project Pit-Claudel that is about automatically generating low-level code from high-level descriptions. Now, with my students, Alexandre and Yawen, we're actually looking at generalizing this, connecting it to a hardware from mixed systems that have, well, various kinds of components, or reasoning about complex data structures. And finally, none of this is usable unless you have the right tools. And so with my PhD student, Chardul, we are working on diagrammatic tools. The question we're asking is, well, when you do math on computers, why are there no pictures? Whereas when you do it on paper, there are pictures all over the place. And so we're solving that question by saying, well, let's just generate those pictures, give users the tools to actually create pictures that accompany their mathematical developments. And then with a student that was in my lab for a year at Basel, we worked on the semantics of dynamic variables. I put this one because I like the name a lot. We call this spooky action at a distance, but it's not the physics version. It's when you mutate a variable here and it affects your program there. And the last part with my student John is we're looking at making these automated math provers, these things where you plug in the formula and they say yes or no. We're trying to make those more reliable and more predictable. And so with all that, I would say that by nature, software programs should be some of the, if not the most reliable artifacts ever produced by humans. Where other engineers must test their work, formal methods give us software engineers the tools to completely eliminate implementation mistakes. And yet, this has not happened. Software engineering remains a profoundly experimental discipline, and we have an abysmal track record for security, safety, reliability, and trustworthiness. My claim is that we can and we should do better. Thank you.
Thank you so much, Clément, for this inspiring talk. Questions, please. Linus.
Yeah, thank you very much for the talk. I think I got 3/4 of the way through the talk, so that was very nice. Just the example you gave with uppercase and the corresponding C program, so there's a potential buffer overflow in there. Where do you manage that one?
That's a very good question.
So, I mean, if you give in a pointer and just the length, I mean, the length might be good or not.
Yep. So here's the thing. There's a slight simplification in the way the specification is written. But the idea is that in a typical, so here, when you have this curly brace, those curly braces at the top are doing a lot of work. What's happening here is I'm saying two things. First, that the pointer that I named as a string here, but usually would be a machine address, is pointing to that string S. And if you unfold this little arrow, logically what it means is so S is a logical value. It's a pure string. There's no concerns about overflows there. It's a logical model of a string. But then what this arrow says is there are as many bytes allocated as the length of the actual logical string. So this precondition says you may not call this function unless the pointer S has memory that exactly corresponds to the logical model. And then the len parameter here, so here's the thing. In the logical world, you can ask for the length of the string. In the physical world, in the low-level world, you cannot ask for that length because, maybe your string is your terminated, maybe even not. Maybe it's just, you have n bytes, and that's why you're passing that len parameter. But then you run the risk, as you said, of what if my parameter goes out of sync with my string? And that's why here, we're not saying len is an arbitrary number. We're saying len is explicitly encoding the length of the logical string. So the specification guarantees that these two things cannot get out of sync. Now, the funny thing is I said I generate C. If you take that function, the one that gets generated at the end, there's nothing, there's nothing here that prevents you from calling it with incorrect parameters. In fact, you can't even at runtime check that these parameters are correct. Again, you cannot in C check whether you have the right number of bytes. But the thing is, so if you run this program standalone, then you have to be careful to satisfy the assumptions it was verified under. If you're wiring or linking this program with another program in the context of that verification, then it will force you to actually ensure that these preconditions are satisfied.
Thanks a lot.
Any more questions?
Hi, great talk. So in your journey to get people to write better, more provable code, what do you think is going to happen with now people just relying on ChatGPT to write their code?
Well. Give me 1 second. Can you believe it or not? I have backup slides. How good is that? So I didn't pay him to do that. So here's the thing. There's basically two problems. Let me just skip to the answer to that question. There's two problems with the way we do AI programming. If you think of software, 50% is writing, 50% is code review. Now, there's a thing called Amdahl's law that architects like, is if you make 50% of the system take 0 time, then you're only 2x faster. And that, well, it's debatable whether ChatGPT makes the implementation 0 time. I would say, not clear. But even if you had the perfect ChatGPT that got things perfect every time, you still have to review the code. That is, you still have to convince yourself that the code does what you ask the system to do. And that review process actually gets harder when you take machine-generated code. It doesn't tend to make the same mistakes as humans. So we're in this weird situation where we can generate a lot of code very fast, and then try asking one of your colleagues, please review these 20,000 lines of code that were just magically written by an AI. It doesn't work well. So the pitch here is, if we have a nice formalism to express what the program is supposed to do, then what you can have a machine, it could be ChatGPT, it could be code synthesis, it could be any technology you want. It doesn't matter. What matters is you have a generated program that should correspond to a specification. You can essentially automate the process of code review using formal methods. So the hope is that, so a lot of industry is working on this essentially automated code review with verification. One place another place that's actually, well, there's something happening for this at EPFL is for math. So now that we've said code is math, you can go the other way and say, well, math is code as well, right? So that means that you can write programs to actually prove theorems. And so there's a whole branch of math that does this. And then, well, if you have AIs that can write code and code can prove theorems, well, can't we have the AI prove the theorems that way? And the nice thing here is that if we have proof checkers, that is, if we have things that say, well, is your proof valid or not written in this fully formal setting, then you can actually get an AI to generate your theorems and the proofs, not the theorem, and then get your proof checker to say, okay, well, the proof that the AI gave you is not complete nonsense. So I think there's a brilliant future for formal methods in the brave new world of AI.